Welcome everybody to this primer sponsored webinar. I'm Vince Neary. I've been working in marine energy at Sandia for about 8 years now, and previously from Oak Ridge National Lab. And I'm going to be presenting with my colleague Ryan Coe, who's been at Sandia for about 8 years as well. I want to first thank Haley and the primer team for hosting this and providing all the support to make this happen. We have an hour, of course, and so the format of this webinar, I'm going to provide a pretty abbreviated overview of the project, some of the background on this seedling project for 2020. And then we want to spend most of this hour going through a demonstration, which Ryan is going to drive. We're looking forward to your questions. We're hoping to have about 10 to 15 minutes at the end for questions and answers. But I want to, ask you to use the chat on the Zoom app to, write out your questions as we're going through the presentation. There's also a survey. Haley provided the link to that survey in the chat. And so we're looking forward to as much feedback. That's really the main goal of this webinar. So the topic here is, as I said, this was a 2020 seedling project. These are small amounts of funds that are provided to the labs to do some initial investigation of, potential efforts, projects, studies. And in this case, the idea was to scope out the workflow, functional requirements, and graphical user interface for a web app tool designed mainly for technology developers to build, analyze, and archive design load cases that are spelled out or specified in the International Electric Commission 62600-2 technical specification. I'm using standard loosely here in this title. And this is a very important technical specification. It basically is what developers have to use to determine the requirements to ensure the structural integrity and safety of their marine energy conversion devices. So this could be anything from a wave energy converter or what we call current energy converters, which could be in tidal currents or river currents. This work was done in collaboration with the team from BIBA, the University of Bremen. That includes our co-PI, Andy Hasselsteiner, who's joining us here. Andy has a lot of experience and has done a lot of great work in a lot of this, developing a lot of the statistical methods that are used in this tool. And he and Ryan are actually currently working on a benchmarking study with experts like Lance Emanuel at University of Texas, Austin, benchmarking the environmental contour methods, which are used heavily in this technical specification. So if you could go to the next slide. So this tool, we feel, addresses the challenges that we expect technology developers are going to have as they work through this very complicated technical specification. There are about a dozen design load cases that have to be evaluated, and it's a very complex analysis, iterative process that has to be gone through. You have tasks ranging from finding and downloading the best available data to applying complex statistical methods, characterizing site load conditions, and modeling your environmental condition inputs into your dynamic simulator tools or models, which could be numerical or physical models. And then you have more statistical methods that have to be applied to your device load response to eventually get to your design load requirements, which are needed to certify your device. So it's a big lift. It requires a lot of staff and staff time and resources to go through this. And so, you know, we want a tool that is going to streamline that process to the extent possible, you know, really provide support for technology developers, especially. There's also an opportunity, we feel, to integrate a lot of the legacy models and tools that have been developed by national labs and others. So, you know, we have, for example, models like TurbSim that, you know, could be thought of as environmental conditions models that then are fed into a dynamic simulator model for a hydrokinetic turbine like OpenFast or Cactus. And we have other efforts that have been done previously, one led by Ryan, actually, which was the WEC Design Response Toolbox, the WDRT, which can be incorporated into this, this web app tool. If you go to the next slide. So we felt that the best way to address these challenges and, you know, the opportunity we have here to integrate tools was yeah, through a web app tool. As I said, you know, the main goal of this is to streamline the design process and also to provide a single workspace where you can, you know, collect and archive your site data, your design load case parameters, and all the device load response statistics and design load requirements, as well as providing some, you know, facility to generate reports that can be, you know, there could be like a boilerplate report that can then go to say a third-party V&V group like DNVGL to evaluate and make sure that everything looks good as part of the certification process. The very important requirements or functionality, or well, requirement of this web app tool is that it's aligned very well with the -2 technical specification, obviously. So that gets down to the details of, you know, using the exact same terminology and everything, so there's no confusion, you know, in following through the -2 standard. And then there's a number of functionalities or capabilities that I'm listing here that we wanted to include. I don't want to go through the details of the list because I want to save time for Ryan to demonstrate these. But, you know, and of course, these slides are going to be available for everybody so they can, you know, look through these details on their own when they have more time. If you want to go to the next slide, Ryan. Yeah, and so the target user, as I said, our target users are mainly technology developers, the staff that are going to be doing the design following this -2 standard, of course. We want to design this tool for a range of design experience and skills. So, you know, the tool is also, you know, it's heavy on helping the designer navigate through and providing a lot of guidance as to, you know, what is the most appropriate, you know, the best, say, statistical method to select given your data source and other, you know, attributes of the data that you're using. However, you know, we hope that we would see users as well in academics, university researchers and national lab researchers and others, you know, that are interested in design or some aspects of things that this tool can do, like finding the best available data sets for a marine energy site. If you could go to the next slide. Right, so the workflow can be thought of in very basic terms for this tool as, you know, there are two basic processes that are wrapped around the dynamic modeling that's done to, given the inputs of the environmental load conditions, you have outputs of the device load response. So there are two types of sessions that Ryan will demonstrate with this tool. You have what I would call pre-dynamic model sessions, which are all about characterizing the environmental loads, for example, the wave loads or hydrodynamic loads with a current device, modeling those loads as inputs into the dynamic simulator, This could be, I think I've mentioned, either a numerical model, like WEXIM, for example, or it could be a scaled model, a physical model experiment. The -2 allows the developer to use, a numerical or physical model. And then, of course, those models generate what we call load response results. These are time series that show, that output the loads on various components of the device. And further statistical analysis is needed, like the WEC design response toolbox methods that Ryan and others developed, to determine your characteristic load. And then you apply your partial safety factors in the -2, and you get your design load requirements. And so this is needed, of course, to satisfy the standard and to certify the device. Another aspect of this that is not in the -2, but we hope to incorporate at a later date, is the device classification. So that's something we're going to be working with the IAC with to incorporate that in a similar way to the design standard for wind turbines that some on the webinar might be familiar with. If you go to the next slide. So next steps, before I turn it over to Ryan, we want to propose a sapling project. So this was a one-year effort, really just to scope the workflow out, as I said, and develop the GUI. Now we need, with a sapling project, if we're successful, we can build in the functionality that's needed, that is kind of illustrated with this GUI in the demonstration. This demonstration you're going to see is just for to illustrate this process for a wave energy converter, but we'll need to expand this, of course, to current energy devices in tidal and river environments. We'd like to do case studies with developers, ideally, possibly with other efforts that are going on in DOE through Primer and MHKit. I understand that there's some interest in, going through this process and getting a feel for how, things like data availability and how difficult it's going to be for developers, working in certain sites, and whether they'll have issues with data availability. And then finally, starting with this webinar, we would like to get feedback with user surveys, and so hopefully, we'll get a lot after this call. So with that, I'm going to turn it over to the demonstration. Oh, sorry, I just want to end with acknowledgements. We had a lot of help from others, actually, besides the project team, Sterling, Kelly, and Katie Kleiss at Sandia. There's some, we're leveraging some tools that have been developed actually or available now in MHKit, you'll see, for like the data QAQC. And then, of course, we want to thank again Haley and her team, Liesel, Garavelli, and others who helped to announce this webinar and put it together. So Ryan, if you want to start driving.
Sure. Can you hear me okay?
Yeah.
Okay, awesome. Thanks very much, Vince. Yeah, so I'm super excited about this tool. I think, as Vince mentioned, I have a leadership role in developing the next edition of the -2 specification for the IEC, which this is built around. And as someone who's worked on editing it and drafting it, I can say it's very, complicated. I want to try to simplify the document, but I think it's still going to be a challenging thing to implement. And yeah, I think a tool like this can really reduce the burden on everyone and kind of allow people to do what-if studies and look at different sites and design optimization much more fluidly. And so I'm pretty excited about this idea. So yeah, this slideshow, which Rachel Ahn and Lena Stower, I think, were primarily responsible for putting together, kind of mimics a graphical user interface that we would have for this web application tool. We have underlying code to execute the analyses, but it's not necessarily wrapped with the GUI at this point. This is just sort of a emulation. But I'll walk through an example here In this case, we are Walter Wave, a wave energy developer, but we could be Olga Wind, a wind energy developer, or Ted Tidal, someone who's working on a tidal energy device. So he's going to sign in. He's previously worked on a project in the North Sea, but he's going to start a new project. It's going to be a wave energy converter project, and he's going to call it the RM3 WEC for the reference model 3 that was developed a couple of years ago. And now he needs to figure out where he wants to put this device. And in this case, he's thinking about going to Packwave South. So here's the latitude and longitude for that location. And then he can zoom over on the map to that spot and get an idea of what he's looking at. So right off the bat, you can see where he is relative to everything else and start to see what's available in terms of data. Anyone who's tried to do a study like this before probably appreciates the challenge that there is in getting quality data. The good news is that there's a lot of data that's openly hosted by different government agencies out there. A lot of it is not really as easy to get as you might hope, at least in my experience. And so we really hope to streamline that process and make it much more easy to look at different locations fluidly. So this is this little marker here is exactly where Walter wants to go, and the closest point to data point that he has to that spot is some data from the DOE SWAN hindcast simulations. You can see that the period of record goes from 1979 to 2010. There's the Packwave North site nearby. Remember, he's going to the Packwave South site, so that's why he's not right on top of that. He's looking around the area. Maybe he wants to know where he's going to have some final assembly done on his device, and he can see that here's Newport, Oregon, and there's a marina there, and there's the Port of Toledo, which contains a couple of shipyards and shops where he could get work done. And then there's other types of data as well. We've got NDVC buoys here, so there's a couple of those in the vicinity that he might be interested in, and they all have different periods of record. So you can see like Stonewall Bank, for instance, has about 25 years of data. It's fairly far away. This NSF buoy is closer, but it only has 4 years of data. So could weigh that. Here's another buoy that's a good bit further away, only 3 years of data. So Walt decides he's going to go with the hindcast data in this case, and he's going to use the SWAN hindcast data. I should have mentioned that all the points on this grid, basically the fine points, are the hindcast, the SWAN hindcast that's recently been completed for the West Coast, and then the coarser points are the NOAA WaveWatch 3 data set that has been available for a bit longer. In this case, he wants to use that SWAN data set. It's a nice long data set, high quality. And so he's going to pull that into his analysis. First step, when you're working with someone else's data, especially, or even your own, if you're me, you definitely want to do some QAQC on that data. Make sure it's not all just zeros or NANs or something like that. As Vince mentioned, this is a good example of a point where we're leveraging existing tools. So we're not having to develop the underlying code to do this. We're just basically creating an interface. So we're going to be using MHKit and the QAQC tools to do this. We're going to just look for missing, corrupt data, things where like you've got a wave height of 100 meters. That's probably a little bit fishy. And you can set what those would be. So, okay, we know that the SWAN data set, for instance, you could know, oh, they use 999 to designate missing values, for instance. And if we're talking about wave period, anything above 18 seconds is maybe a little bit fishy in terms of peak period.
Hey, Ryan, can I just interrupt for a second?
Yep.
Yeah, I wanted to highlight for the audience that, we're tracking the workflow on the left of the slide, or the GUI. So, one aspect of this is it's, the user knows kind of where they are in the workflow. So just so you can kind of keep track of that green dot as we're progressing through. Yeah, that's all.
Thanks, Vince. That's a very good point. Thank you very much. Yeah. So far we've chosen our site. We're doing data QAQC just to let you know where we're going. Next, we're going to look at some statistical analyses, and based on those, we're going to be able to construct some design load cases, and then we'll be able to actually figure out, okay, we need to design the device to handle 6 meganewtons worth of mooring tension or whatever it might be. So finishing out that QAQC, we can do some initial checks, just algorithmically, everything looks okay. It's always a good idea just to look at things visually as well and see if you've got any crazy jumps or something that might not get picked up via the algorithm. So we can do that here. The time series, another nice plot to look at often is a scatter diagram of the period versus the wave height. That looks reasonable. That was peak period. Now here's energy period. That also looks very reasonable. So we're going to move on to the next stage here. We think our data is good, and we're going to start looking at some statistical analyses. By the way, I should have mentioned, if you have questions while I'm talking here, don't hesitate to go ahead and post them in the chat. If I see it, I'll try to address it immediately, and if not, I'll come back to it at the end. Okay, so now we're at the statistical analysis stage. And you can see over on the left here, a bunch of different condition types, basically. For instance, we've got the significant wave height for 1 and 50-year return periods. And each one of these is a component that's going to help you build a design load condition. So in the example today, we're going to look at DLC 6.1, which is the extreme wave load condition. And so that's got your 50-year return period extreme sea state. And there's 2 ways to get at that I'll demonstrate. And it's got a couple other components to it as well that are important. But anyways, DLC 6.1 is the one that we're going to work on at the moment. If we scroll down, we can see, okay, there's, some other important factors, wind conditions, things like that as well. Yeah. Okay.
And
so
just to mention real quick there,
yep.
Another important aspect of this GUI, this tool, would be, populating the environmental variables which characterize, the loads, the environmental loads, of course, but there are other parameters too that are used in these as variables in the design load cases to characterize the design loads. So I don't know if you showed that, Ryan, but how the boxes, once those variables are estimated or assessed, they are archived, and you get a green check indicating that they populated. You'll see that hopefully with the next.
I'll show that in a second.
Yeah.
I think maybe another way to say that is like some of these things are used more than once. For instance, so like the 1-year significant wave height shows up in multiple DLCs. So you don't have to do that every time. You can do it once, do it well, and then reuse it. So as I mentioned, there's 2 ways to get the 50-year extreme sea state that are suggested in the -2 specification. The first one I'll show, and I guess one of the key things about the DLC generator that we hope to do is provide a kind of a range of methods. Some of these methods are pretty darn easy to implement, others are harder. But one of the key things is that it's generally hard to say this one's going to work well all the time reliably. And so it's useful to have a number of different approaches at your fingertips that you can look at and compare results from and get an understanding of what the range is and how they compare. So we have a couple of different methods for predicting the 50-year extreme wave height here. And you can see kind of how they each perform. Those of you who are familiar with extreme value analysis might recognize that these quantile plots, maybe this annual maximum one looks the most attractive to you. And I'll maybe come back to that if people have questions, but I'll keep moving here. Brian Rosenberg asks, is it possible to calculate a user-specified return period? Yeah, totally. I mean, in the sense that the slides today are as real as this may look, and I think Lena and Rachel did an awesome job. This is not an actual GUI. These are PowerPoint slides. So yeah, I think we can definitely enable people to calculate ad hoc return periods. Good question. So anyways, we're going to work with this exponentiated Weibull distribution, which is the default in this example. And we'll take a closer look at it. We can see the mathematical formula behind it. And Walter decides, yeah, I'm going to go with that. One thing that's important to mention here is that in this case, you're basically predicting what the 50-year extreme significant wave height is, and then you're just going to use a range of periods based on this empirical formula. So you're only really looking at one dimension of the C-state scatter plot, if you will. So now over on the left here, you can see we've populated these kind of components, and we can move on. Another approach that we might want to use is a joint distribution approach in which we produce an environmental contour. And as with the univariate approach that we just talked about, there's a number of different ways to do that. And here's just a couple of examples that we plan to offer. In this case, we're going to look at this method here that Andy Hasselsteiner has used in his 2020 OMA paper, which is quite good. Here's what it looks like in detail. And I should mention, just for anyone who's interested, there's just to kind of give you an appreciation. These are the statistical models, basically, that we're going to fit, the parametric statistical models, and then just to give you an appreciation for the number of options that are available for each of these methods. In addition to selecting a statistical model, you also need to define how you're going to construct the contour based on that statistical model. And all of these selections will give you potentially a range of different answers. And so that's why we think it's pretty useful to equip a user with all these options so that they're not stuck with one of them because it's the only one that they've had time to implement. I think that's quite powerful. And so we select that method for constructing the contour, and now we've got this nice blue curve here that basically shows the envelope of C-states that we expect with a 50-year return period. And the idea with a contour method is that if we go to run some simulations or some wave tank experiments with our device, we need to run a couple of points along that contour and see which one is the worst. And so, you know, we've got a couple of discrete points here. You can choose the number of points, and that's left open in the -2 at this point. So Walt's going to save that, and he's going to keep moving. Just to get an overview of where he is, you can see we've got these different design load cases. You've got things like start procedures, emergency shutdown, survival conditions, transport. These are all the DLCs that you need. As you can see, they have environmental components to them, but there's also a device state component to it. This gives you a better view of DLC 6.1 that we're working on right now. So you can see we've got the wave conditions, or the 50-year extreme C state, the current conditions, or the 5-year extreme current state. Haven't populated that yet, but let's just assume that we did. And you've also got to look at the extreme water level range. So you need the tidal information for your location. You've got different partial safety factors to apply. And then there's an extreme 5-year wind condition as well. So you can imagine, you know, pulling all these things together, and even for me, at least, remembering all these different components is challenging. And we really hope to, ease the burden on everyone if we can. So now we've got basically a description of the conditions that we want statistically, or, you know, in block terms. You know, we want basically these significant wave heights and these peak periods we're going to have to look at. But you can't necessarily run a simulation or a wave tank experiment just with a significant wave height. You need to have an actual like time series wave. And so we've got a couple of different options here, which align with the -2 specification. So you can do regular wave equivalents where you use twice the significant wave height. You can use irregular waves, so like an idealized spectrum. That's kind of the most obvious one. Or you can use focused waves as well. So Walt says he wants to go with the irregular wave. You can use a wave spectrum. Right now we show a couple of idealized spectra that he might choose from. Generally, we would also implement like a empirical arbitrary spectrum if you have, if you have spectral density data from the site, which the Hindcast does at a number of virtual buoy sites. And then you also have to look at a time length realization. That's important as well. We can talk about that if people are interested. I think Walt wants to do a John swap though. Seems like a pretty sensible choice if you don't know much else. So we go from our contour, irregular wave. Now we're gonna generate all these C states, or at least this one for now. So let me step back here. Oh. So Walt populated C state 10 here with a peak period of 13 seconds and a significant wave height of 14.5 meters. That is a big wave. Currently in the -2, there is no device classification set up, but it has been proposed and will be considered whether to adopt such a classification like is done in wind. The idea being that you don't want to design a device and or do a design load analysis for every single device that you put in the water if they're a couple miles apart. And so in this case, basically we're going to round up from 14.35 meters to 15 meters. And so now he's got his time series wave here for 3 hours. So he's going to run like a full scale simulation, I guess, probably. And now he can export the results as like a CSV file, for instance.
And Ryan, I just want to mention
download.
Here, I just want to mention again with the workflow, if everybody looks at the top, you'll see there's another kind of workflow diagram, and it's DLC realization is highlighted. So again, this is the kind of pre-processing on the input side of the dynamic simulator that we've done so far. So now Ryan's going to download this, this modeled input to the WEXIM simulator, and then take it from there. Yeah, but you kind of have to stop, download the data and then exit. Now you've finished this session, you're going to exit, then you're going to do physical modeling, whatever, for a few days, and then you're going to have to come back with the results.
Yeah. Thanks for that reminder. So there's kind of 2 discrete sessions imagined with the DLC, and we just finished the first one. Now you've got your C state in hand. Go out and simulate it with Proteus DS, OpenFOAM, wave tank test, whatever you want. Get the data or the response that you're interested in. Let's say we're interested in the force of the PTO in this case. And then you're going to come back after you're done with that. Here's another way of looking at that again. So we pulled in our data, we checked the data, performed statistical analysis, came up with our design load conditions. Now it's time to go run the simulations, perform the experiments. That's your thing. We're not going to play in that field, and then come back with your results. So now Walt's logging back in. He had a great time at the wave tank post-pandemic. He needs to upload his data. So in this case, we say, okay, upload the load responses CSV file. If you want to have some nice visualizations, you can upload a STL CAD file also. And so he's basically got a time series of PTO force at this time, let's say. And he needs to figure out, okay, what is the number, which number of PTO force do I use? Do I just use the maximum from that? You could do that. That's not a super rigorous approach. I mentioned before he chose a 3-hour simulation. And really he should do like 10 of those perhaps, and then maybe choose the maximum from those. But I guess the short answer is there's a lot of different methods here. None of them are definitely right. So it's kind of worthwhile looking at a couple of them. And so we're going to take that time series and try to process it down to a statistical distribution and then pick a characteristic extreme from that. So in this case, he wants to use block maxima. And we can see some statistics about the responses that he uploaded. He's looking at the excitation force and heave, and then the excitation force and surge in this case, and these kind of might be representative of the mooring force in his case. And so we get a characteristic extreme from the block maxima method, and then we kind of come back and apply those partial safety factors to it. And you can see what the numbers that he would use in his design load analysis are. Yeah, and he's got some different bodies here for the PTO and SPAR, and he's looking at those individually as well. I mentioned TTO Force as being another interesting response that he might be considering here. He's just got a single partial safety factor in this case. Yeah, and that is a very abbreviated, very quick overview of a single sort of run through of the design load case generator. And yeah, I've noticed a couple questions in the chat and realized I was kind of getting off track when I was answering them in line. So I'll go ahead and come back to those now. And if you want to add any of those in, please do. And I'll also just kind of replug the survey. If you're so interested, we'd be really happy to have your feedback and thoughts. I've just pasted the link for the survey into the chat. And so if you want to take a look at that while we're going through questions here, that'd be great.
Hey, Ryan, are those directed just to you, the questions? Because I'm not seeing a lot of questions. So
I am getting some directly, yeah.
It'd be good.
I'll read them.
So if I could ask everyone, if you are going to do the chat, yeah, do it to everyone, so everybody can.
Okay. Yeah, that's good. So I'll read it back. Elias Greenbaum asks, how far below sea level do extreme wave heights penetrate? If you're willing to unmute and correct me if I'm not understanding your question right, that'd be great, Elias. But I don't know, the sea surface has like a zero mean. Oh, go ahead.
Can you hear me, Ryan?
Yeah, go ahead, please.
Okay, great. So the question is, you've got all this extreme weather on the surface. Is there any hiding space if you go, say if the wave heights are 30 feet or 50 feet, but you go down 100 feet or 200 feet, is there any mitigation of the damage that they can do?
Yeah, totally. I guess one kind of way I always think is interesting to look at it is that the energy in an ocean wave decays exponentially as you go down in the water column. So at least for a linear wave. And so the deeper you go, the less energy there is. It's a double-edged sword in terms of we're kind of here to collect energy, at least for the wave energy converter. We're here to collect that energy too. So
sure,
yeah, I think generally people understand that. Yeah.
Okay, no, that's good news. Great. Thank you very much. Appreciate it.
Yeah. Just to add to that.
Question.
Yeah, just to add to that, Elias, this design load case 6.1 is specifically for the device in survival mode. So parked or survival, and that's in the description if you go to the -2 technical specification.
Oh, yeah.
So for instance,
yeah, this
there
could be
some people who are considering like pulling their device underwater when a big sea rolls in. Yeah.
Right.
Good. Thank you. Thank you very much.
Thanks for your question. Jay Mearns asks, does the team have experience using visually recorded data, for example, wave simulation films from the Huntsville, Alabama Army Corps of Engineers hydraulic lab to derive time series information from the model input? That sounds very interesting. I got to say, I've not done anything like that. Vince, you want to add anything?
No, but yeah, please contact us. And
yeah, that sounds like maybe a sidebar would be appropriate if you want to reach out, Jay. What other statistical distributions are available is what Navi asked. Yeah, I think kind of similar to like Brian Rosenberg's question earlier, like he asked, can you do this? I mean, really you can't do anything right now because there is no tool. It's just a emulation. But I mean, there are, pieces of code underneath this that we're using ad hoc to produce the results. But so there are quite a number of statistical models that you can use. I'll just say, like, for the contour method as an example, Andy, Lance, and I have been leading an effort where we're looking at comparing a bunch of different methods, and we got 11 unique contributions of methods that people consider to be worthwhile at this point. So there's a large number. I guess I don't know exactly how many we're going to incorporate in the initial release of the DLC generator. I hope that we can do a pretty good number.
And just this might be a good time, Ryan, just to mention or highlight, I think I already said it, but we hope that one of the values of this tool is that it can guide the user who may not even be as familiar with these different methods, but what is the best method that you should be using? And there are a lot of things to inform that decision. One is the data source I mentioned, the period of record. In this case, we have a hindcast data set with well over 20 years of record. And so what's interesting here, this is the perfect plot to show, some might be surprised, but the annual maximum method, which is one, in the family of block maximum methods, actually looks the best when it looks, fitting the data, the tail of the distribution in particular. So we also have a variety of univariate methods, which this demonstration focused more on the bivariate and developing, going to the contour method. But there are a lot of things, and a lot of the guidance is given in other useful design standards out there, like the environmental loads standard by DNVGL, which is probably, the one I'm most familiar with and most comprehensive. And so, we see like little notes and information that we would have in here for the user, and flags maybe if they use, say, they went with the wrong model, So for example, if an example of that would be somebody uses the annual maximum method with only 10 years of record, that would not be appropriate. And it's not allowed actually by the standards.
Mm-hmm. That's, very good question. We're getting lots of good questions. Thank you very much. I'll get into them. Burke Hales asks, what is the ratio of computation time to simulation time? Does it take 3 hours to simulate 3 hours of wave conditions, 3 days? Yeah, this is a very good question. And the answer is it depends, as with most things in engineering. I can tell you, like, a tool like Lexim runs like maybe in good scenario 10 times faster than real time, I think, sometimes closer to real time. If you're talking about CFD for 3 hours of simulation, you better be ready to wait around for like 3 months maybe. So, and the reason I say that's a good question is a lot of these methods are basically intended to give you a more efficient means of getting at an answer. So, I mean, really the most robust way to get to a solution is, if you've got 10,000 points here, is to simulate each of these 10,000 points. And if each one is a 1 hour measurement, then you're talking about 10,000 1 hour simulations. With any tool, that's going to be pretty challenging. Well, frequency domain tool is possible. But if you go to a contour method, then you're talking about maybe a dozen points that you're going to run, these points on the curve here. Now it's getting more tractable that you might run this in CFD or in a wave tank or something. So yeah, really relevant question. And kind of a lot of the reason behind many of these methods is the need to reduce the number of cases that you look at. Jonathan Colby asks, are you going to do a similar demonstration for current energy converters? No one likes current energy converters, Jonathan, or not. I'm just kidding. So we did the initial kind of scoping of this with wave energy converters, but yes, we definitely want to expand it to current and tidal and even offshore wind. Even if you're a wave energy converter developer, this is actually beneficial to you because, as you'll notice in some of these slides, there are wind and current conditions that go into the DLC, into the DLCs for a wave energy converter. So they're overlapping here. 62600-2, the design specification, is across all of the MHK device types. And so, yeah, I guess I don't know if we'll do a demonstration in the near term, but we are definitely interested in working on a current energy converter version. Sorry. Someone maybe go on mute. Okay.
Yeah, so again, just to clarify Jonathan's question, or to respond to Jonathan's question, you know, that is the next step. Yeah, hopefully if we can get a sapling, that's one of the first things we want to do. So, you know, at the same time, we're building in the functionality for, you know, these analyses that Ryan went over with this demonstration for a WEC. We want to do that and build in the functionality at the same time for a tidal energy converter. I think discussing this with the group, we feel like, you know, with leveraging a lot of the functions that we've gotten, things like, you know, MHKit and WDRT, and tools on the current side with like TurbSim, that you know, ideally we could get that done in a year, I believe. So, you know, that would be the hope, and that maybe this time next year we'd be talking about, you know, we showed this demonstration for a hydrokinetic turbine.
Yeah, that would be really cool.
Ryan and Vincent, this is it's very nice that outline the boundary and the wave excitation. I wondered, did you use the tool to go through detailed design of the components? For example, no matter which concept you choose, PTO or modern system, to say how large the system will be. The reason I ask you, because like the 50 years wave, the type of thing, the plus safety factor, you design all the mechanical system is very, very bulky. Did you use this tool to go through some particular concept?
Oh, yeah, so we did kind of use the components of this tool to look, we used it with the reference model 3 device, the 2-body point absorber. But honestly, that's a pretty minor aspect of what's been done here. So yeah, like this device. Most of, yeah, I mean, really the entire tool is built not around the device, but around the conditions and the statistical analysis. So it's not really device centric, I would say.
I know, but this tool will be used to guide the device design, right? So this,
sure.
This is what we are struggling in the existing project. When we use the safety factor, whatever percent together, is very, very bulky.
Oh, yeah. Well, actually, I would totally encourage you to, I'll reach out to you, and we are currently working to revise the -2 specification. And I'll say that the partial safety factors in there are based on offshore wind, and there is lots of room for reconsideration and refining those. So yeah, we don't determine any of the partial safety factors as part of this project. We're just basically implementing and creating an interface to the -2 specification. So yeah, I'll reach out to you, and I'd like to talk about that more.
Okay, thank you.
Phil says, yeah, it looks great, and thank you very much, Phil.
Giannis here, maybe quick question. The tool uses quite a number of existing tools that you mentioned, like MHKit. Is everything you have available outside MATLAB, for example, in Python? Because otherwise, if you were to have a cloud hostess, you might run into license issues with MATLAB.
Yeah, everything that we've utilized so far is in Python. And I guess, I know some people like Andreas and the other folks from Bremen have experience with Django and building web interfaces for Python programs. That's going to be one of the next things we look at. But yeah, so far we're pretty good in that respect.
Okay.
Yeah. How much sensitivity is there to device and mooring specific factors, e.g. hull shape, tether drag? This is from Burke Hales. Yeah, definitely. I mean, like the response of the device, yeah, is very device dependent. I mean, I'll give one example, for instance, like the contour here. You might immediately think that this red dot is the most important point to consider because it's the biggest wave. But of course, the different systems are going to respond differently based on the frequency of the waves, and also the steepness of the waves, it's related to the frequency and height. So, you know, we've had these smaller waves down here, but they're fairly steep. Those might be problematic for, I don't know, slamming and the like loading on the hull itself. But then these longer waves out here are probably going to excite the mooring system more, and those might be problematic. So yeah, like my previous answer, I guess it depends. Ford asks, for multi-modular deployments, can the tool account for wave dissipation before reaching the target model? Not in this case, no. I guess probably what you would want to do there is use something like, and there's a fork of Swan called SNL Swan that can remove energy from a wave field. That would kind of be really in your device simulation stage. So, I mean, the tool exists, you know, produce the wave condition, or not the waves, but the mid-ocean conditions that you're considering about, and then post-process the results. And probably that would happen in this middle point here where you're simulating, which is the area that the DLC generator does not play in.
Hey Ryan, sorry to jump in here. This is Burke.
No,
but my
go ahead,
question
Burke.
about the device sensitivity, I'm trying to figure out where in this you must put some sort of simulated body into the model in order to generate loads, right? If there's no load, if there's no body there, there's no load. If there's a body there, there's some load. And so what is that? That's sort of what I'm after. Did you just put a generic geometry of a certain size,
yeah.
Or where is the?
So sorry if I was moving too quickly. So I mean, first off, we worked with this reference model 3 device in the upper right-hand corner of the slide that I'm pointing at. It's a 2-body point absorber that was developed under the Department of Energy. It's a pretty large device as far as devices go. That's the one that we used in the example here. But I'll just kind of try to reemphasize that the sort of device response aspect of this is the part that's outside of the design load case generator. So we generate like the inputs to that model, you know, how hard is the wind blowing, how big are the waves, and then you go with that RM3 model or Aqua Harmonics device or Oscilla Power device, you go run your experiments. And that's the part that's device specific. You go run your experiments. They could be numerical experiments or whatever. And then you come back with some time series, and that's where you start up the DLC generator again. Am I answering your question? Oh, great. Thanks, Burke. Yeah, it's a bit of a kind of, I think it's tricky, or at least it's an important concept, and make sure we find a good way to communicate that. Are other environmental factors considered, e.g. main current wind? Yes, definitely. That's super important. Right here, we focused a lot on the waves because we just had to focus down on one thing for time's sake, but all these design load cases have quite a few aspects to them. Yeah, here's a good slide for that. So up in the upper right-hand corner, you can see the relevant components for DLC 6.1 that we use. And you can see there's quite a few. I mean, I'll tell you, like, you could probably get most of these conditions from any of the hindcast or wave buoy data, but as far as like the current conditions and then the wind condition, you might be challenged to get that data from a single source. So you're probably going to point from multiple sources for a lot of these design load cases. And then beyond that, there's also the device condition, which is like parked or survival condition in this case. Awesome. Thanks, Burke. Gary Ross asks, our development is close to shore. Is it possible for your generator to consider tide? Yeah, definitely. And that's related to the previous question. We do plan to consider tide. And as you can see here, water level, then you need to consider basically the extreme range of the tidal water level. And I guess if you're talking about current as well, then it would probably be captured under the current conditions.
Yeah, what we were trying to spell out here is, most of these DLCs are combined loads. So, and all those details are in the -2 document, of course, and we're just kind of laying those out here. And yeah, just for the purpose of, doing this in a time efficient way, we just went with just assuming just the wave load was the only load operating.
Yeah. Walter asks, have you developed a module for QAQC current energy converters yet? No, but I think kind of related to the previous questions, you can kind of see, and if you look at the -2, you'll know this. Kind of once you do wave or tidal, you're going to be most or all the way there to doing QAQC. So at least if you do it completely, as we have current conditions, for instance, in this wave device DLC. So yeah, I think as Vince said, I think there's a decent chance if funded, we hopefully have all 3 MHK type devices ready at the same time. I don't know, maybe a year from now, and hopefully offshore wind as well.
One thing that is a little more challenging with the current side is we model the environmental wave load condition, the input that goes into, say, WEXIM or dynamic simulator, just using a simple modeled spectra and then an inverse Fourier transform. In the case of currents, we would ideally use a good tool like TurbSim, which was initially developed for wind turbine design. But you can think of TurbSim as almost like an environmental load conditions simulator, right? That provides the inflow inputs for designing a wind turbine, or in this case, a hydrokinetic turbine, right? And then that would be, simulate your inputs to a model like Cactus or OpenFast. And then you get the design load response from one of those models. And then come back in with those device load response time series and do all the statistical analyses on that to get your characteristic loads for the various components, and then apply your safety factors to get your design load requirements.
Brett Swain asks, can you add your actual wave device with another energy converter? Mine converts wind, hydrogen, and solar. I would like to add motion. I think this kind of relates back to one of the previous questions where like the actual device modeling step in this process is not part of the design load case generator. So you're generating the inputs to your device model, and then you're working with the outputs of your device model. So that's probably more of a like WEXIM or open foam type question in this case. But as far as like the conditions that you would need for that, yeah, this would work for you. Solomon Yim asks, the tool is excellent and very useful. In the extreme wave case, linear wave theory should probably not work well. Are there efforts in nonlinear wave model development? We were hoping to use your work on that, Solomon, I think. I'd say we hadn't thought too much about that at this point, but it would definitely be something that we would be very interested in incorporating. I'd say general sort of approach in this tool is leverage existing work that's already out there and bring it together. So that's a great point.
Thank you.
Yeah, thanks, Solomon. Brett Swain asks, my Powerball would have to connect to the top of the waves to collect the wind power, but it could store energy made by your wave generator at the same time and take water in and convert. Same thing. Could use the tool to do simulation of other systems. Yeah, I'll just kind of, again, it's not really for doing like dynamic simulation. It's about getting the inputs and working with the outputs of those simulations. So I think it could be, sounds like it could be useful for your application. Walter asks, in one slide you showed OrcaFlex. Is OrcaFlex related to Orca 3D marine software? I'm actually not familiar with Orca 3D, but OrcaFlex is a Morrison model / potential flow model for simulating device dynamics and ship and offshore platform dynamics. And it's got a particularly good model for mooring dynamics as well, as one thing it's popular for. It's basically a way for you to look at how your floating body would respond in waves. I probably should know what Orca 3D is, but I'm not familiar with that one. Christian Williams asks, hi, tried searching for app using DLC gen, not luck. Any ideas? Yeah, sorry, Christian. This tool exists only in a set of PowerPoint slides right now and some Python scripts and things like that. So if you are excited about this, strongly encourage you to check out the survey that I'll post again into the chat, and let us know that you're interested and the specific things that you're interested in. Yeah, at this stage, we basically scoped out what this would look like and what the workflow would look like. And next, we are very, very excited to actually implement it and put together a tool. So with your enthusiasm, I think hopefully we'll get a chance to do that.
I know we're we're over time by a few minutes, and so we probably bring this to a close. I just want to encourage everybody again to fill out that survey. We intentionally made it brief, so it's it's only a page, and that really helps us to improve the product if we get the opportunity to work on this more. So, but really appreciate all the feedback that we've gotten just with the questions, and I think hope there will be this presentation is recorded and will be available, I think, through Primer, and as well the slides will be made available, the PowerPoint slides, so people can study those in more detail. And I don't know, there might even be another opportunity to do another webinar, but so yeah, thanks again, everyone, and look forward to seeing some of you that I recognize in meetings in the future. Thank you.